as you can see, this is not John Avina hosting. This is Bob Vorwald hosting today. Today's Abraxas webinar is going to be a little bit different than what we've done in the past. It's going to be a pseudo debate here. Does AI really work for buildings? And this will be, this discussion will take place between Duane Warren and Keith Gipson. They will be questioning each other back and forth, and a large portion of this will be focused around optimization, building automation systems. Looks like Keith is coming up on the screen. And if everybody's wondering why I look like I'm in a uniform today, I am in a uniform because directly after this call, I have the privilege of being on an honor guard about half hour after this call's over. Keith, how about, since I got you visible right now, I'm going to let you kind of give yourself like a 2-minute introduction of yourself there.
Certainly. Thank you. Pleasure to be here. I'm very excited to participate and be a part of this webinar. I'm the CEO and founder of Facil.ai Corporation, and we develop autonomous AI agents to run buildings and optimize them automatically with no humans in the loop.
Thanks for that brief quick introduction. And Duane, if you are on the audio, if you could give yourself a couple of minute introduction, please.
Sure. I'm Duane Warren. I'm the engineering director in the Sustainability Services Group in JLL. I'm a licensed refrigeration mechanic and mechanical electrical engineer. I've been doing optimization for, I don't know, 20 odd years or so. And this marks year 46 for me in the industry. So
46. You've outdone me by 6 years.
Yeah, me too. I just turned 64, and I've been doing it since I was 24. So I've been
I won't count my I won't count my teenage years.
Yeah,
so with that, I appreciate everyone here. A lot of the attendees on this call too have, like I said, decades of experience in the field of building automation and energy conservation. With that, I am going to give Duane the first go with the start of this debate. So I am going to mute myself and also turn off my camera so I'm not distracting y'all folks, and you can go ahead and have this discussion. So Duane, if you want to get things started.
Sure. So one of the things that we got asked to do is to provide 3 questions for each other, and I sent those out last night. So one of them, the first question I had was, how does your system deal with intermittent failures caused by poor wiring or connected BMS devices and controllers, or bad mechanical design or installation issues, which we run across fairly regularly?
Yeah, excellent question. I'd like to share my screen to answer that. I get asked this question all the time, and I really believe a picture is worth 1,000 words. So let's go to, I'm on my website right now. We have a couple case studies of some central plants and a large retailer. Let me home in on this with going to Channel Islands. So this was I call it the 48% savings in 48 days. This is a central plant, CSU Channel Islands. This was beautiful because we actually had a catastrophic input failure. We started off with the PID loop only. So I always frame our solution as it's AI versus the machine, the PID loop. It's not AI versus humans. Humans are not scalable. You know, I'm really up against a PID loop that's sitting there 24/7, 365, optimizing, controlling a plant. I'm helping that PID loop alone. So the humans aren't even really involved in this process. Think of it like a supercharger for a car. It just makes it run better. So we started off September 30th at 1.2 kW per ton at Channel Islands in their central plant. And you can see the first 7 days, the system started learning about the operation of the central plant. It started after about 10 days, it got down to about 33% energy efficiency gain. It went from 1.2 to 0.8 kW per ton. And yeah, we're on our way to, tracking 40, 50% savings that we usually do when something catastrophic happened. There was actually a chiller mechanic working at our site. And the first indication was that the condenser water temperature went up to like 89 degrees. And the chillers went offline, everything crashed. So of course we had just put our AI in a couple of weeks before. So immediately it was like, what did your AI do? Why did it raise the condenser water temperature up to 90 something degrees or whatever it was? Of course it didn't do that. Yeah, there was a chiller mechanic working on one of the chillers and he basically blew the chiller up. So there was a problem at the site. We had catastrophic loss of our meter, which is the main input that the AI uses to optimize the plant since it's driven off of kW per ton as a goal and not just a temperature, an arbitrary temperature goal. And yeah, we lost connectivity to our meter. The AI lost connectivity to its main meter for 7 days while they replaced the meter. And then something amazing happened. The AI actually fell back and used the previous week as a guide, as a proxy to controlling the central plant. And then you can see after the meter was replaced and it got back on track, there was a little bit of relearning outside of that red box, but the AI still was keeping the plant running at a 33% energy efficiency gain. So what happens when AI has catastrophic loss of sensors? It's a better out. We're not going to say nothing happens, but it's a much better outcome if it's just a human there. And then ultimately it relearned, and 40 days later, it dropped the KW down from 1.2 to 0.62. It had learned how to control that particular plant. It had mapped it out on its own, built its own model, and we saved 48% for the second time in a row on our last two central plants. So that's what happens when we lose sensors.
All right, so, just to summarize, that means it continued to operate, just adapted to the fact that it did not have certain sensors available.
Yeah, player piano mode, I call it. So imagine if you lost your eyesight and you had been driving to work for 1,000,000 years and you were taking the same route, all other things being equal, if you could time your turns and speed, and you could maybe you could hear the cars coming. You had superhuman hearing. You're Superman. You could hear the cars coming. The AI is going to naturally fall back and use whatever sensors it has available. It's the same thing with Tesla. So Tesla they have full self-driving, unsupervised, and rolling out right now. It's got 12 cameras around it. What happens if it loses one of the cameras? Nothing happens. It's like an octopus or something. Like it sees like multiple keys all the way around. It's not going to be optimal, but it's certainly better than what would happen if a human optimizer had catastrophic loss of a sensor input. Because a human can't remember every single adjustment for the last, 2 days, 2 months, 2 years, or 200 years, like AI can.
Okay. Duane, how's that cover your question?
Yeah, I'm more concerned with which we see at JLL pretty regularly. I'm more concerned with bad installations. The BMS has got intermittent sensor problems. Maybe it can't map properly. Sometimes they're not wired correctly. Things of that nature. We see a lot of that.
Okay. Yeah, that was your second question, I believe. So let me answer that one. We see this a lot. So of course, you're going to have 20 to 25% of the portfolio is going to be miswired, undersized, oversized, under refrigerant charged, all that. To answer that question, I'm going to turn to another customer of ours. It's a large retailer that has 2,000 stores across North America, about 8,000 rooftop units. We save them $200,000 to $1 million a month with perfect comfort and reduced maintenance costs of about 30%. This is what it looks like. This is it sits there round robin. I'm going to restart it so you can actually see the process, how it works. But yeah, I'm in kind of like debug mode. I want to share this log with you so you can see what actually happens. But while that's firing up, yeah, the system actually goes round the clock, optimizing all of the sites, and out of the site, the system actually goes back to it pulls in all the stores, and so out of 6,000 rooftop units, it only really is optimizing 75% of those, because about 2,000 of them, 1,500 to 2,000 of them have problems, just like Duane mentioned. You're never going to have a perfect portfolio. At my last company, Phoenix Energy, we had 20,000 buildings connected, retailers of various kinds, and I can tell you that the best data quality we could get was 80 to 85%. So yeah, we don't have to optimize the whole portfolio. We only optimize what we can optimize. And so to answer your question directly, what do we do with those buildings that weren't put in correctly, have faults or whatever? Nothing. The AI does an assessment of each and every unit, and if it's not, if it has any sensors missing or it's not working properly, the AI has already done a baseline of each and every unit, built a model, so it knows what correct operation for that unit. So if it's broken when it happens to go by that unit to optimize it, it just moves on to the next one and checks it back in another couple hours. When it gets back to it, and if it's gotten fixed by then, it'll optimize it. If it's not fixable, then it skips it, and it'll keep doing that as long as it takes. We're looking at the portfolio level for our solution. It doesn't have to have perfect systems to do a great job, and it's a tremendous amount of ROI based on our system. We've been there for 4 years. Yeah, we're not going anywhere. We're saving them millions and millions of dollars. And I always say, like, what those systems that are broken, that's not our business. We're an AI optimization company, not a fault detection company. That's for Tritium, SkySpark, Clockworks, whoever you want to name. That is not our business. We'll be happy to refer our customers to them.
Hey, Keith, if you want to go ahead and ask some questions of Duane, go ahead.
Yeah, thank you. Yeah, I'm interested, and I'm not, let me say right up front, I'm not disputing that, Duane is a brilliant, engineer and knows what he's doing. The point I'm trying to make is that the question, I think the title of the debate is like, does AI really work in buildings? I think we've already answered that question. We're saving our customers, again, millions of dollars a year. We're making their buildings run better. So I don't think that's up for dispute. I think it's a contrast and comparison of where AI runs out of steam and is not appropriate for it. It's definitely not appropriate for a system that needs a tune-up or needs to be recommissioned or redesigned. That's not our business. We're here to optimize the 80% of your portfolio and your central plants. And honestly, you don't see many central plants that have problems like I have. So maybe one central plant out of 100 might have serious problems. Central plants are mission critical applications. They have to function. They have to function properly. They get the tubes punched every year and all that stuff. So that's not really a thing. That only happens with RTUs and air handling units. But mission critical central plants, yeah, they're up and running, albeit not that well. So ASHRAE says that standard performance in a central plant is 0.7 kW per ton. Better is 0.65. The best you could do is 0.45, and we routinely achieve better than the best of the ASHRAE 90.1 standard when it comes to central plants. So yeah, I just want to get an idea of what your process looks like. I don't have any information like what type of results have you achieved when you're optimizing a central plant, for example?
Yeah, so typically, typically we get most of the work that we're doing, almost all the work is in central plant chilled water system work. So I wouldn't, and we're pretty careful not to call it central plant work. It's actually, for us, it's actually chilled water system work. And I can tell you that our experience, without question, it's more the inverse. Maybe 1 out of every 10 or so central plants that we look at are actually working correctly. And when I say correctly, I mean, hey, you can start the chillers and they run and the sequence works and things like that.
Okay.
So we're usually seeing plants that are, up in the 1.2 to 1.5 kilowatt per ton range. And, if there's poor chillers there, one of them can't run, they can't seem to make it work, things like that. So
Okay.
that's typically what we see, and that is, and this is kind of I would characterize this by saying that one of the reasons it's a broad-based problem that is not either one of our doing, but it is, I guess, an opportunity in some ways. Uh,
We
uh,
see, not to cut you off, but we see plenty of plants that are in the 0.7 to 1.2 range. I just showed you one, and that doesn't mean that there's anything catastrophically wrong with it, other than the control sequence is saying that we should keep the condenser water temperature at outside air web
so
flow.
I'm gonna continue to answer the question.
Yeah.
So so generally what we do is we want to make sure that we can get the equipment working properly. And it's not necessarily just a central plant problem. Generally, it's some sort of problem outside the plant, problem with air handler control, pump control, cooling tower control, things of that nature. And typically we'll see when we're done, we will see. I don't know if I'll make the effort to share my screen, I suppose. So primary, secondary, tertiary loop, and it started out at about 1.3 kilowatts per ton. We have a 4-stage operation, so we want to get load side management working correctly. And then we have some staging operations that we do that gets us into a mode where we can start doing high side control and module integration after that. So we do find that fault detection has some bearing on what we're trying to do, particularly when it comes to things like refrigerant loss in chillers. Typically, if you have a chiller that's got for every 1% loss in charge, it's 1% less capacity, 1% more power draw. And depending on what kind of manufacturer and what kind of chiller, some of them, leak like a colander in the rain, and some of them leak a little bit, but they all leak. There's no way around that problem. And we look at bearing wear and various other things that are part of fault detection. And when we looked at developing this process, we looked around at SkySpark and some of the other things, some of the other fault detection routines that are out there. And most of them don't really do the kind of fault detection that we want to see. So what we want to see when we produce a fault detection issue, something like a sick chiller or a refrigerant leak or something like that, we want to produce a statement that the end user, the building operator, is going to be able to take to a service mechanic and say, this is what we're seeing. And so these are the initial steps. Typically, they're the initial steps that a service mechanic or a service technician is going to take when they're trying to figure out what's going on with the machine. And so they actually do a module integration and fault detection, actually do produce savings for us. This particular plant is 4 chillers, 4 2,000-ton machines. They all have VFDs on them. They're not mag-bearing machines. And the plant, including cooling tower, condenser water pumps, and chiller pumps, is running at 0.307 kilowatts per ton. And so you can see the chill water stuff energy is blue, chiller energy is red, condenser pump energy is green, and cooling tower energy is purple. It's a little hard to see, but if you look at the ratio of cooling tower energy to chiller energy from the beginning compared to the end, you can see that the ratio of that cooling tower energy is a little bit higher down towards the bottom. So we're making the cooling tower run a little bit more than the but on a percentage basis, it's running more than the chiller power is using. If that makes sense, we're trying to run that smarter. So
it makes perfect sense because all the numbers that I'm quoting are always at the total plant level. So our AI that's precisely what it's doing. It's leaning more on the chiller or the cooling tower and finding that inflection point between the efficiency curves. Not a straight line, it's not linear, it's a curve. And so, yes, it's constantly finding that sweet spot between using chiller energy versus condenser water. I would like to point out, not saying that you're doing this, but what I've seen in the industry is that people laser-like focus on just making the most efficient part of the puzzle, the chiller, the most efficient. So they focus on at the chiller. It's almost myopic. So they're trying to make the chiller. I mean, but the AI is coordinating all that. It's acting as an orchestrator between all. Whenever I talk about a 48% reduction, like you saw at Channel Islands, that's overall plant power, because we total up all the KW for all the equipment, including the chillers. So, and we're routinely achieving, 47, 48% efficiency gain at the plant level.
Yeah, going after I get it. Like a chiller is kind of, it's a big machine. It makes a lot of noise. Everybody wants to tame the monster, but all that stuff works together, right? So I will say that although I haven't run across your product, I have run across other systems that claim to be AI, and really they're not. They're just curve fitting software that and I have to be careful because I can't actually legally name the company that I've had to fix, but I've actually fixed 3 of their installs and removed 2 of them. And so I understand how they work very well.
We've seen the same thing, by the way.
Yeah, and if you're trying to drive from San Francisco to Boston and you start out driving towards Mexico, bad things are going to happen. You're not going to get there. And so if they start out going in the wrong direction, I guess maybe they'll find something, but it's not going to be useful. So
if you don't mind, Duane, you brought up a very good point. I'd like to kind of expand upon that. You talked about going, if you're trying to go in one direction, you end up going another direction. The concept of guardrails and safety limits frequently comes up. I just came out of about a month ago. We talked about why we took the guardrails off of our AI, and it's exactly what Duane just mentioned. The difference between artificial intelligence and true artificial intelligence, I'm talking with true deep learning and machine learning, like a self-driving car. So it's the same thing. This is full self-driving for buildings. The AI, the way AI artificial intelligence works, and more explicitly machine learning, is that it has a goal and it's going to relentlessly drive toward that goal, and it knows what getting better or worse looks like. So when people talk about these extreme guardrails on the system, those are, first of all, those are already in place. They've been in place for 40 years, with I always call it the Commodore 64 that's hanging on the wall. So, I mean, they've always been there. So central plant, you don't want your condenser water, for example, to go below 60 degrees and certainly not above 90 degrees. So yeah, that's a hard limit. Never go down below 60 because it's not going to be psychometrically advantageous. And you certainly don't want to go up above 90 or so degrees. And so, yeah, those are hard limits. Our AI doesn't even get close to that because it's not beneficial for it to do it. So when a chiller starts getting distressed, an amazing thing happens. Its KW per ton starts going up, not down. It's telling you it's groaning pain. So it knows, I know what a happy chiller looks like. And, Duane and I can both talk about that for years. The AI does as well. So it's going to incrementally make small adjustments, safe adjustments, stuff that is seen in the past, and it's going to draw from that experience. We don't get even hardly close to that 90-degree upper limit. So it's, the max will be like maybe 78, 80 degrees. And it certainly is not going to, the only thing you're going to do with the cold water is you're going to maybe some chillers, you have the older ones, you have oil migration, stuff like that. So the AI is smart enough to understand when the chiller is happy and when it's not happy, and it drives toward that goal in a safe and secure manner.
Yeah, we may it depends on the plant, but we may go down as low as 50 degrees on condenser water. Depends on the plant. And in some cases, you may catch from my accent, I'm originally from Canada. In some cases, I've actually run the plant inverted. So I've had condenser water colder than chill water supply. And
Yeah,
you can do that.
Yeah, you can't go. I mean, of course, you can never go below outside your wet bulb because that's psychometrically impossible, right? So yeah,
Right. Right.
we use outside your wet bulb as a proxy, or the AI does that because it's constantly looking at, it's the law of physics, right? I mean, you're trying to help that evaporation process. People also ask us what inputs that we use for our AI. It's a lot more than the building control system. I'll give you one example. So everyone knows that a cooling tower is pretty much an evaporative process, right? When's the last time you saw wind speed and wind direction on a building control system? You think that wind might have something to do with the evaporation at a cooling tower? Of course it. So our system, and this is another reason why you can't run AI on the edge in the Commodore 64, or maybe it's up to 128K of memory. You don't have the bandwidth, you don't have the supercomputer in the cloud to bring in a NOAA weather feed from 2,200 NOAA weather stations around the country like we do. You don't have the input, you don't have the point of sale input or Google traffic for retail stores like we do. So the AI is it's a correlation engine. It's taking in hundreds of variables, stuff that doesn't even exist in a building control system, to map out that one control output. So there's a one control output, and people say, oh, you're only changing the set point. Well, yeah, but look at all the up to hundreds of inputs and number crunching that's going on to get that precise adjustment. That's the difference.
Mm-hmm. Yeah, we'll do something similar with optimizing set points in the cooling tower. We're looking for lowest power use in the plant. And that cases where we're dealing with lower condenser water, typically that's situations. I try to avoid it, but in some situations you can't. You'll have an industrial site where the cooling tower is remote from the central plant, and it's wintertime, and you don't have a choice. The water's coming from the cooling tower, and it's 38 degrees. Fans are all off. You got a bypass going, but it's cold enough outside that it's freezing. It's getting the water down. And if you bypass the tower too much, the tower freezes up. So you got to run water over the tower to prevent it from freezing, and blah blah. So you end up with cold condenser water. You got to figure out how to deal with it, right? So you can do it. You can do it. And in some cases, we look at situations like that where we'll say, hey, maybe you need a fluid cooler here. But we find when we do that the use case of that fluid cooler compared to a chiller running at that colder condenser water is pretty remote. Like the chances of you being able to say, hey, I'm going to save enough money putting in a fluid cooler when I'm running a chiller down at 0.18 kilowatts per ton, you got to have a pretty cheap fluid cooler to make that work. Because then if you run the fluid cooler to get the water down cold enough, you gotta do funny things with the tower. You start using a lot of tower energy.
I think I see a lot of questions in the chat. Do you think we want to start jumping on some of these questions?
Why don't we go into a few of those, because there's some interesting ones. One of the first ones that came in, and I think it might be on a number of people's minds, is, okay, how do you interface with the existing controls, or are there specific vendors that have AI enabled controls or anything of that sort, or how do you bring in that external portion in the AI?
So we got two ways to answer this question. I'll tell you the experience that we have with existing BMS vendors that do this or purport to do it. And I will tell you that without exception, all of the existing BMS contractors that say they do this kind of stuff kind of somewhere between don't work very well and fail spectacularly. And get to a point where we get to a point with them where we're saying, look, can we please just get your stuff connected so that we can actually see the damn points? And so that is a huge struggle from the existing BMS group that do this sort of stuff. Typically, unfortunately, the result of that with most owners is that they tend to put in an overlay and think that this is a problem they can solve by using Niagara or some kind of overlay over that, and it really doesn't improve it. And it may be that the options for that are doing something like what either one of us are involved in, making the damn thing work, right?
Right.
But because I've worked with all the three big companies that are involved in this with all of their AI intimately, what they call AI, and it's not really. It's a bunch of PI loops with some nice looking graphics and a monstrously huge feed. So that's my take on it.
Okay, can I answer that from my perspective? Can I share my screen, please? And Duane's right. So first of all, I'm going to answer the second question first. I haven't seen any AI-enabled building automation system. I don't even know if that exists. I do know that Framebox. I'm not sure how much they're incorporating that into their next generation tracer. But
it's not that great.
I haven't seen that, but yeah, I can't say that, but but yeah, maybe, but I don't know, but I haven't seen it, so that's so obviously this is the elephant in the room, right? Connectivity is poor. We don't depend on the incumbent vendor. Why would we? Sometimes we're in an adversarial competitive situation. But actually our story is a better together story. So we're not competing with JCI and Honeywell and Trane, and all the other vendors. We're an overlay, and the only way you're going to be able to accomplish that is to be able to get to the data. That connects another point. There's a lot of AI companies, and I'm doing the air quotes on purpose, that are saying that they're using digital twins. Let's get this right out the way right up front. The reason that they're doing simulations on a simulated piece of equipment is because they can't get to the damn data, as Duane said. So if they could get to the data and the real-time telemetry in real time, they wouldn't have to do a simulation. Imagine if you went to your doctor and said, I'm having chest pains. I really need you to help me. I'm scared. And they say, okay, great. We've got this new AI digital technology. Here's a facsimile of your building, of your body up on the screen. And we've done all these tests on this virtual simulation of you, this synthetic data. And I think we got the right choice. We're going to have to operate immediately. What would you do? You'd walk out. There's no way that anybody can simulate a human body like that, at least not yet. Just same thing with tornadoes. You can't simulate a tornado. The way you learn about tornadoes, you can do your little simulations all you want in math lab or whatever, but the way you learn about tornadoes is you get within 100 yards of them and you throw a bunch of physical sensors into it and you drive like hell to get away from it. That it's the same thing. You cannot model the complexity of a central plant. No one can. At least not with the technology that we have right now. I can tell you at our sites, chiller number 2 is distinctly different than chiller number 3, which is different than chiller number 1. Same chiller sitting right next to it. I don't know if it's Jupiter or sunspots. I don't know what it is, but there's something different about each machine. So the only way to do this effectively and to get the numbers that we're getting is to have the AI learn the heck out of each individual machine and build its own model and train itself. And as far as connectivity, I've had this list up on the screen for a couple minutes now. You can see that we cover virtually every building control system out there. These are print drivers. These are software gateways. My wife just got a brand new printer. She wanted to print out her pictures. There wasn't an install process with the printer. She just plugged the printer in and it worked. It's the same thing that we've done. So it's not a heavy lift. These are true plug and play. We call it our interoperable software stack, or ISS. And that is available you know, some people are engaging with us not even for the AI, they just want the connectivity.
Right. And so from our perspective, we try to make our offering run on the existing automation system.
Yeah, we do too, always.
So it just runs good or bad, however you want to put it. Everybody, when we're finished with the installation, everybody's smarter than when they came in.
Yeah.
So the automation people know how to run a chiller plant. The people in the building know how to run the chiller plant. They all know. Our aim when we're finished with the training procedure is that if you're in the site and when we walk away, you're going to be able to implement the same process in a plant on your own.
So buildings have been wasting, to that point, buildings have been wasting 30, we say it all the time. We've been saying this, we're used to it. We're almost like immune to it. Like it's dead to us. We say buildings control, you know, 40%, they have 40% of all the energy and they routinely waste 30% of that. It's like a parrot or something. Like, what are we going to do about it? So the only way to, in my opinion, the only way we're going to do something about that is to earnestly apply smarts like you know, Duane, my team, and Duane and his expertise, and also use digital technology, all the digital technology like AI, like machine learning, like fault detection, all kind of stuff. But we've got to earnestly apply technology to fix this. We can't just, to Duane's point, we can't just replace systems. That's not going to work, because you're just going to replace it with another system that's marginally better than the old system that you had in there, because it's still controlling it to outside air wet bulb plus 5 degrees, which doesn't.
Yeah, I'm reminded of Chuck Yeager. Everybody have heard of Chuck Yeager, right? But one of the flights that Chuck Yeager went on before he broke a sound barrier it was the second flight before that. While he was flying, one of the control handles that he was using broke off. Imagine that. And that's kind of what these building people are like, right? They've replaced an automation system with another front end, and it's a wipe over the top of it, and the old stuff didn't work, the new stuff doesn't work, and they're just, you know, they're moving away at warp speed, and they got no way to control it. They're just
Duane, I've seen, I'm sure you've seen this too. I've seen vendors get a shiny new BMS, and the new vendor couldn't understand the complex sequence of operation for the static pressure control, and they actually replaced variable speed drives with fixed speed drives.
Yep.
And they're gonna say that they're saving energy. How the heck can you save energy if you took out a variable speed drive? It makes no sense. So yeah, I agree.
Physics gets in the way. Physics gets in the way.
Can't beat the laws of physics.
Yeah.
See, I wanted to try and read through one of these questions. I get they're a little tricky to read. Let's see, efficiency and optimizing. Let's see if I can read this question. How does bad information, miscalibration, etc., how is it addressed if you have a bad data set from sensors not calibrated? So they're there, but maybe they weren't calibrated correctly to begin with.
This is a great question.
Yeah.
Let me address this because AI does a great job. It's not even looking at the number on the wheel. So let's say, and so I was a service tech. You're talking to a service tech from 40 years ago. I know how buildings work. When they go out of calibration, it's a sustained deviation. So it's not like they continuously go out of calibration. So people ask this question all the time. The way this works is, let's say you have a sensor and you've taken a bucket of ice and you dropped the sensor in there, and it's going to read 32 degrees or thereabout. That's how we used to calibrate sensors back in the day. We drop it a bit, maybe we might still be doing that. I don't know. I've been at tech for a long time. Let's say you drop it in a bucket of ice and it's reading 3,200 degrees. So it's out of calibration. If you raise the temperature up by 1 degree Fahrenheit, instead of reading 3,333 degrees, it's going to read 3,300 degrees. Does it matter in the big scheme of things to figure out how that system is running? It does not. It doesn't matter what the number is. The AI is just twisting that knob. In fact, the numbers are irrelevant to the AI. It's looking at the knob twist. So if I turn this knob, whatever it's reading, 5.5% in this direction, what happens to my goal? Now, if your meter's out of calibration, yes, you're going to have it, but it's the same thing. Let's say it's reading a million kW instead of 1 kW. Doesn't matter. The AI is after that number going down or up. So it's the order, the magnitude doesn't matter. It's the trend and the direction. It's directional. So I get this question all the time, and it is irrelevant when you're talking. It doesn't.
I would disagree with that, and I would disagree with it because we have buildings that have requirements for they're medical buildings or the medical research buildings, and they're federally mandated audits.
That's not calibration. That's precision.
Yeah, well, it kind of is, because if you're supposed to supply 42-degree water, you better supply 42-degree water.
Yeah, those are two different things. I'm talking about optimization versus a precise standard, which has to be. And in most cases, what happens, Duane, the sensors are calibrated to a NIST standard or something like that. So that's all built in. So again, the sensors are not going to be out of calibrated. To my point earlier about the mission critical central plants, they're going to be calibrated because they have to be calibrated.
We just don't see that. You know,
Yeah.
we run it. You expect that those facilities are going to be in a state where calibration occurs, you know, once a year, once every 6 months, maybe once every 2 years on the outside. But you know, we regularly see meters, sensors, and meters. And meters are a very good example as well. You know, I'm dealing with 4 plants right now, 4 buildings right now, where the power meters in the buildings are 10 years old or older, and they are no longer accurate.
It's not necessarily a bad thing. So yeah, I've seen 20-year-old meters that are more accurate than the fancy new ones. But yeah, continue.
Right, but they're only they're only rated for you know, when the manufacturer says, hey, past 5 years, all bets are off, and might still be accurate, but might not be too.
So back to my comment around resolution, remember, we're talking, when we casually say, we saved them 21 kW. Oh, oops, it was 20 kW. 1 kW is 1,000 watts. So these watt meters have to be within, I'd say within 1,000 watts of the real number before it even matters. Because we're measuring it, the unit is so large. It's 1,000 watts. So if I get with it, if I have a meter that has a resolution of 500 watts, that's that's darn good enough to do an assessment when you're talking about thousands of watts.
Yeah, we're talking about power meters that are off by 10-15%. So we want to see that information coming back.
Up there,
I want to see that.
I've seen all that.
Yeah, we want to see that information coming back correct for the and as correct as is practical. And you know, if there are wiring issues, which we normally see, we see a lot of that. You know, you see sensor wires run parallel to power wiring, things like that. So we want to see that kind of cleaned up, and we want them to get the automation system that they paid for originally, and get that working correctly. And once that's working correctly, optimizing it is very straightforward.
Yeah, you seem like they're really like that's actually electrically illegal. Like you can't. I mean, you both of us know you can't run low power and high power side by side. At least you're not supposed to. So these are edge cases. I'd like to you know. Well,
that is not an edge case, my friend. I bet I see that on at least on 3/4 of the installs that I'm looking at.
Where you got low voltage wiring inside high power wiring conduit?
No, it's not. It's not inside the conduit, but it's wire tied right to it, or run right next to it for a couple hundred feet. Yeah, you know, either tie wrapped or wire tied. They'll run 2 conduits.
I'm just saying, man. Okay, I haven't seen it really that high, but yeah.
That is pretty scary.
Oh, they
Our time is coming close, so I'm going to interrupt with another question I saw here that I thought might be interesting. Is that aside from products like what you're working with, Keith, your product line, have either of you seen cases where owners are implementing their own AI, taking advantage of trying to implement themselves, utilizing something like Claude or something like that? Have you come across that and had a, well, if so, was it good, bad, or ugly?
Okay, I'll take this one. This is right in my wheelhouse. There's 3 different types of AI. There's generative AI, which is ChatGPT. There's predictive AI, like TensorFlow, and then there's inference AI, prescriptive AI, like ours. You are not going to get ahead by trying to hook ChatGPT up to and say, ask it what the optimal temperature is for the condenser water given the inputs. It just doesn't work like that. You know why? Because again, it's built on a model. Where did all the information come from for ChatGPT? It came from the ignorant masses of control people out there that don't know that they shouldn't be running their plant in the correct way. I guarantee you that you will not be able to have ChatGPT would never be able to match the performance of our prescriptive AI that's custom built and patent pending to control a central plant. It's just not even close. So yeah, you're not going to be able to do that with generative AI or even predictive AI.
Okay, Duane, have you seen anybody try?
Yeah. So I've seen several attempts made at it, and in fact, within GLL, different people have tried it, and it is like trying to hug a porcupine.
Are you talking about Hank AI?
Yeah. You don't get me started on that thing. So what I would give you a pretty close analogy for this. If you were trying to figure out where you want to drive today when you leave this meeting, you don't go back yesterday and try and figure out where you drove yesterday to help you figure out where you're going to drive today. That's not how it works. And that's how most of these control systems or most of these AI systems work. They look back at other things that other people have tried. And maybe they might look, if they're semi-smart, they might look back on what happened yesterday to make a decision about what you're going to do right now. And that's not what you do. It's not what you do. Yesterday was yesterday. It's an interesting history.
I may have to vigorously disagree with you on that. That's the essence of machine learning. Is
Yeah,
looking at what's happening. So I mean, that's got a lot of that is a logical fallacy.
So you were using machine learning to make a decision. Yes, AI like Claude does not do that.
Okay,
Claude does not do that. Claude will instead of trying to use that information to make a prediction, it uses that information and says that's what you got to do. And
I thought you were talking about the essence of machine learning, which is forward and back propagation, because that's the essence of machine learning. So yeah, we're definitely doing that.
Yeah, and us old school guys. So I'm an old school control guy. I've done a lot of industrial automation work. But what we're talking about here is actually something called feed forward control. And I've been doing that for 20 odd years. And you would say, hey, that's AI, but if you're going to throw the football to a receiver, you don't throw it where they are, you throw it where they're going to be. And you know where they're going to be based on information you know about how fast they run, where they cut, things like that, right? And so
that's the essence of machine learning is a prediction. Even when you show AI a dog or a cat vision training, you're training it. It's a prediction. It's predicting what the animal is. All AI machine learning is prediction. So to say that you can't look backward on it, like that's the essence of AI. So yeah, we are doing that. In fact, that's why our solution works as well as it does, because it does 288 5-minute intervals every day. So it's after a while, it's tried every combination possible, and it definitely is looking back. In fact, our system actually tells you where it's coming, where it took its prediction from. It tells you moment in time. It's like going back, hey, this worked a year and a half ago, and it seems to be working now. So yeah, that's the essence of machine learning, is prediction.
All right, I've got to jump in here. We're about at the top of the hour. I did want to give it just, we'll go a couple of minutes over here, but we're not going to go very much over because I've got a hard stop personally. But I would like to, for first off, thank both Keith and Duane to get on here and have these discussions because this stuff's coming one way or the other, right? It's either going to be good, bad, or ugly, and we all see all facets of that. I like seeing that, okay, if we're going to implement advanced controls routines and AI into our systems, let's do it, let's share what we're learning through these mediums, and find those that are doing it good work out there. I don't think Keith would be had a bunch of failures and then and would be on here because there'd be too much naysaying going on about his work.
It's on failure. It learns what failure looks like and doesn't do it. I'm reminded of, I went to a real estate seminar, and the guy said, you want to learn the secret to being rich? Here it is. Look at what poor people do and don't do it. That's the AI. We learn from failure.
So
it doesn't work.
With that being said, Duane, any last closing statements you'd like to throw out about good, bad, or ugly, or concerns about AI? Because it's going to be there moving forward. So
yeah. So if you're catching hint of this, it looks like we implement the same sort of thing in both of our activities. I will say that one of the things that I will say is that my screwdriver has never fixed anything, but I've used my screwdriver to fix a lot of stuff. And you will never, ever, ever use a control system to fix a mechanical problem. That is never going to happen. So if you have a mechanical issue, physical issue in the space, you got to fix the thing, and then you'll be able to control it, and you'll be able to use various kinds of AI internally, or like what we're talking about here.
We're agreeing on that. We don't address 70 to 15 to 20% of any system we touch. We leave those for the SkySpark people and techs to repair it and mechanics. So agreed.
Yeah,
that's not our business.
All right. Thanks, Duane. Keith, any closing comments you'd like to make at this point?
Just that AI is here. This is not a philosophical argument. I mean, I'm putting in, we got thousands of buildings under management, and that's gonna, quadruple by the end of this year. So I mean, it's going in.
Okay. Good. If people have additional questions for either of you, I believe Gabriel, correct me if not, that we have they can forward questions to Abraxas, and those can be forwarded out to either Keith or Duane for future questions, comments, or reach out. They may want your help on a project someplace too. So I think both of you would be glad to help. So with that, does either of you have any final comments? Otherwise, we're going to be wrapping this up because people
just to say I appreciate Duane, and man, I love to have a drink with you and share battle stories, war stories and stuff in the field. It's obvious you've been there for a while, just like I have, and yeah, we're both doing great stuff, and I appreciate you.
Yeah, solving the same problem in very, very similar ways, just using a different screwdriver.
Yeah. Absolutely.
With that, I am done. If anybody else has got anything left to do, thank you.
All right. Thank you very much. Appreciate it.
Thanks.
Thanks, everybody.
All right. Thank you.